Okay, hello everyone. Welcome to Lecture 5 of Chemistry 3120. Today we're going to continue our discussion on hydride reducing agents. And if you think of last lecture, we looked at, or we introduced a couple hydride reagents. Those were strong ones like lithium aluminum hydride and sodium borohydride. To recap briefly from last lecture, we learned that lithium aluminum hydride was a very strong reducing agent, and it would reduce aldehydes, ketones, esters, and amides. And sodium borohydride was a weaker hydride reducing agent, where it would reduce aldehydes, ketones, sometimes esters, usually quite slowly, so not very efficiently, and not amides. So we're going to now discuss reducing agents that could have perhaps opposite selectivity. So you might imagine you might have a molecule. I'll just draw this as a molecule. And perhaps you have some type of amide bond that you'd like to reduce. But on the other side, you might have an aldehyde or a ketone. So how do we reduce something like this and not touch the aldehyde? So what we're going to talk about first is a reducing agent called boron, or BH3. So BH3 is, it's a fairly inert substance, and it looks like this in 3 dimensions, and it has this boron orbital here, low energy p orbital on boron. In fact, BH3 is a gas, and it's actually complexed with the structure B2H6, where you have these bridging hydride units and then another molecule of boron next to it. But for us understanding the mechanism, using the structure BH3 is definitely sufficient. So BH3 is actually really good at reducing amides and also other types of molecules like carboxylic acids, but it's very poor at reducing things like aldehydes. So let's think about how that happens. So why don't we take an example of an amide and ask the question, what happens when we treat this with BH3? All right, so like I said before, this is fairly unreactive. However, when you have boron available and you have this low energy p orbital, this p orbital is actually very much attracted to electrons. And where do we have electrons on the amide bond? Recall that amides have good sp2 characters, so you can quite easily draw a resonance structure throwing electrons into this system here, thereby pushing electrons up to the oxygen. So if you imagine a resonance structure breaking the pi bond, you could also imagine that this will now interact with the boron and forming an oxygen-boron covalent bond. So let's see what that looks like. So our boron now has 4 bonds. So in the case up here, it was neutral, but because it has 4 bonds now, this is now negative. We form a double bond here. We now have a positive nitrogen. So I want you to look at this structure here, and I want you to ask, do we have a nucleophile and an electrophile within the same molecule? Well, for sure we do, right? So we now have a negative boron. So these are now nucleophilic hydride units. And what you have here is a positive nitrogen charge with this double bond here. This is our electrophilic carbon. So we can envision now an intramolecular nucleophilic attack from the hydride onto this carbon and then pushing the electrons back to the nitrogen. So if that were to happen, we're going to generate this species here, and our hydrogen unit, or the hydride that we've added, I'll just put in green here. Okay, so now I want you to think back to what we discussed with lithium aluminum hydride with amides. So with the lithium aluminum hydride, we had a sort of a similar type of intermediate, except we had aluminum attached instead of boron. And then we asked the question, which one would donate its electrons? Would it be nitrogen or would it be oxygen? So we know that nitrogen is more willing to donate its electrons because it is less electronegative. So what's going to happen is that you're going to form a double bond, and then this here is going to leave as a fairly good leaving group. So what you're going to have is this here, which is an iminium ion, positively charged electrophile, and what you have coming off is this species here. And this species is actually relatively stable because of the p orbital that I've drawn here with boron. You actually get some electron donation from the lone pairs, thus stabilizing this complex. Okay, so the question I have for you is this our final product? Is the imine our final product, the iminium ion? And remember that when we're doing this reaction, we're going to have a lot of free boron, a lot of free BH3. So this iminium ion is very electrophilic, and the electrons are very willing to actually, donate to something nearby. So in fact, what will happen is we will get electrons here adding to this empty p orbital, and simultaneously you'll get hydride attack occurring at this electrophilic carbon. So you can think of this in a concerted mechanism type of fashion, and what you're going to generate is your structure with a BH2 here, positively charged nitrogen, and we have our two hydride units that we've added here. So at the end of the day, this is going to remain in solution until you quench the reaction. So when we quench the reaction, we're going to quench this with water. Something like water will quench this, and essentially water has those lone pairs. It's going to be attracted to the boron, and then it's going to release off that boron-nitrogen bond to yield our final product, which is an amine. Okay, so we generate the same product like we would with lithium aluminum hydride. However, the mechanism, as you can see, is different. So let me just summarize this reaction because there's a lot of different things on this board. And so just to make it clear, we are taking this amide and it's a two-step reaction with BH3. Typically we do this at low temperatures, something like -70, and then we do a water workup to give us our desired amine. Okay, so that is what we call borane reduction of amides. It's not going to touch aldehydes. The key governing feature is electron donation from this amide into the BH3. So you need electron-rich substrates in order for this to happen. Okay, so let's look at another example of how BH3 can reduce a different functionality. Let's look at the case of BH3 with carboxylic acids. Okay, we haven't looked at carboxylic acids yet, right? But this is another functionality that is often very useful to reduce. So if we take a look at a generic carboxylic acid and ask the question, what is going to happen if we add BH3? And again, use the same principles that we had in outlining that BH3 has an empty low energy p orbital. So one of the first things that's going to happen is that we're going to get one of the oxygens reacting or forming a bond with a boron. And this is governed by electron donation from the other oxygen. So one way to denote this is to have this oxygen come down here, and then you form this oxygen-boron bond, as I'm showing. We now have a negatively charged boron, and we have something that looks like this. Now, we have a nucleophile, and we also have an electrophile here. But what do you think is going to happen first? And the hint is that you have an acidic proton here. This is different from the amide, where you did not have any acidic protons. So don't forget, acid-base chemistry will happen first. So this negative hydride will take the easiest electrophile, which happens to be a proton, and what you'll generate is something that looks like this. And you might say, well, we haven't reduced anything yet, and you're absolutely correct. We've done some acid-base chemistry, and we're setting ourselves up for the next type of reaction. So now imagine you have lots of carboxylic acid molecules, right? So you would have here's another carboxylic acid molecule, and you can imagine that this will come down, and you'll get the same type of reaction occurring just like we did at the beginning. So if this happens, you're going to generate this type of intermediate. Now you have two oxygen-boron bonds here, positively charged oxonium ion, and you're going to do the same acid-base chemistry to give you this product here. So I think you can see the pattern. Now we're losing one hydride unit at a time. So another carboxylic acid molecule is going to come, and the bridging oxygen is going to complex with this, and you're going to get acid-base chemistry. So the steps are identical, so I won't draw how that mechanism occurs, but it's exactly the same thing. Okay, so you have this like triborate complex, as I'm showing you here. And as I mentioned before, we haven't done any reduction yet, right? So how are we going to get things reduced? All right, so what we're going to do is we're going to now have a way and think of how to activate this complex. So instead of me drawing that complex here each and every single time, I'm going to now abbreviate this as I'm going to show. Okay, so this is going to correspond to the same trimer structure that I have in the upper right hand corner there that I've circled. All right, so at this stage here, we haven't done any reduction yet, but keep in mind that we have boron hydride present. Okay, so now we can imagine a case where we're going to get another molecule of boron trihydride reacting and now you have a negatively charged boron, positively charged oxygen. And now I think you can see the electrophile. The electrophile is right here. And this is actually quite electrophilic because normally the oxygen here would be happy to mask that and donate electrons. However, because the boron has this empty p orbital here, it's actually going to move electron density to that central boron, thus making these carbons a little bit electrophilic, or quite electrophilic. So what you're going to end up getting is nucleophilic attack at that carbon, and you'll generate this type of structure here. Now, what's going to happen next? Recall that this OBH2 here, we've seen something similar over there. So what do you think is going to happen? So we now have a system where we have two oxygens, right, who can compete for one another and can donate electrons. Now keep in mind, this is a triborate ester here. So a lot of electron density is moving this way to the central boron. It's really happy to receive electron density from 3 bridging oxygens. Whereas this boron here only has electron density being offered by single oxygen. Therefore, in terms of the ability of the oxygen to donate, or the boron to accept that electron density, this one here is more willing to donate its electrons. Okay, so we are now going to generate a structure that looks like this. Okay, recall that our hydride did attack here, so we don't have to put it in, it's implied, but I think it's easier to see that we've added that hydride. Plus, you're going to generate your boron here with these O negative charges, and it's a trimer. So, what's going to happen next? So I'm just going to redraw this in a slightly different way. So what's going to happen is that oxygen likes boron, and these in solution is going to come, attack this boron, and then you're going to get hydride attack at this electrophilic carbon, and then push electron density up to that oxygen. All right, so if we do that, we are going to have this type of structure here. So now you have this oxygen that's now formed a complex with this bridging boron. We've transferred a secondary hydrogen here. So now we've undergone that full reduction. And then this thing will sit in solution for a while until we quench this with water. And as we've seen before, boron loves oxygen. So when we do this workup step, the water will come react with the boron, and then you'll break that oxygen-boron bond. So that will leave you with this alkoxide, which can then pick up a proton from water, since now we've added water, and your final product is the alcohol. So a lot of different things happening mechanistically here. So I just want to highlight again how boron works and what that final reaction is. So we can take a carboxylic acid and we can treat this with BH3, keep that at cold temperature if you'd like, do the same type of workup. And we generate, in this case, primary alcohol. We'll do a summary of all these different reducing agents at the end of this lecture, but what's important about BH3 is that it reacts with electron-rich substrates, so things like amides and carboxylic acids. So it reacts very poorly with things like aldehydes and ketones. Okay, so let's talk a little bit about something a little bit different, lithium borohydride. Okay, so lithium borohydride that's the structure of lithium borohydride. You know it's a reducing agent because it looks like this. Here's your lithium. And we already talked about lithium aluminum hydride, sodium borohydride. Okay, and the difference between these two essentially is that lithium borohydride reduces esters well, with sodium borohydride reduces esters poorly. Okay, and you might have a situation where you have maybe an ester on a molecule and an amide, and if you use lithium aluminum hydride, you're also going to reduce that amide to an amine. So can we take the best of both worlds and see whether we could have a molecule that reduces esters really well but will not reduce amides? Reduces esters well, and I'll say and amides. Sodium borohydride reduces esters poorly, and amides not at all. Okay, so lithium borohydride. Let's look at how this could react or reduce an ester. All right, so one of the fundamental differences between lithium aluminum hydride and sodium borohydride is the fact that we have a lithium cation instead of a sodium. And the lithium is actually a much smaller cation compared to sodium. So what that means is that it's going to form a much stronger oxygen lithium bond compared to sodium. So what does that mean? So that means that you can even think of this as a covalent bond. And it's going to more strongly activate this complex. Just compare what we learned with sodium borohydride. Sodium borohydride was much bigger, So it forms a much weaker interaction. And you also did sometimes these reactions with hydrogen bond donors to help activate it. Whereas this is a more pronounced and direct way to activate it. So once that's activated, then you have your borohydride reagent. It's negatively charged, and the electrons will go up, react, like I'm showing you here. And you add a hydride equivalent to that molecule. At this stage here, you know this is it's not a great leaving group, but it's good enough for the system we're using. Electrons will come back down. You'll kick off your alkoxide, and you generate an aldehyde, right? And you have your lithium back out in solution. And recall that aldehydes are more electrophilic than esters. So once you get to the aldehyde, you're just going to take another molecule of lithium borohydride, and this will come and react really quite nicely. You'll get your 2 hydride equivalents, and then when you do the workup step, this will react with water to generate your primary alcohol. Okay, so lithium borohydride, maybe I'll write something up here. It reduces esters well, and of course aldehydes and ketones, but amides not so well. So maybe just to summarize that reaction, and since I have this space here, why don't we look at the ester, lithium borohydride, and then water workup. Okay, so I just want to show you a specific example of the chemoselectivity between lithium borohydride and BH3. Okay, so if we take this molecule here, you can see it has a carboxylic acid, there's a stereocenter here, and then here we have an ester. So let's go through this. So BH3, as you know, will react with carboxylic acids to generate alcohols. It will not react very well with esters. So that product will look like lithium borohydride reacts well with esters. We just went through that mechanism, but it will not reduce carboxylic acids very well. So what we will end up generating here is a primary alcohol. Okay, so now if we take these two molecules and if we treat them with some catalytic acid, and if we look at this one first, if we add acid, we can imagine protonating here, this coming and attacking. We generate a 1, 2, 3, 4, or 1, 2, 3, 4, 5, 6-membered ring, which is favorable. And we could also imagine this group coming off. So we'd undergo some type of esterification. And the molecule that you would get would be an ester, an intramolecular ester, which is also known as a lactone. So let's draw what that is. There's your lactone. If you do the same thing over here, you have a carboxylic acid with an alcohol catalytic proton. This undergoes something called Fischer esterification. And you'll also generate, in this case, a lactone. Your lactone will look like this. Okay, so we can generate two different products. However, you can tell that they are isomers of one another. Right? They're in fact stereoisomers. And more clearly, they are actually mirror images of one another. So these are enantiomers. Okay, so using chemoselective reducing agents allows for the creation of unique stereoisomers, as is shown in this example. Okay, so we have one more type of reduction that I want to talk about. For some reason, this wants to go up by itself. So I guess what that means is I'll erase this, which is not a problem. Okay, so the last one I want to talk to you about is a compound that's called DIBAL, which stands for diisobutyl aluminum hydride, or DIBAL-H reduction. So what is this compound? It looks like this. So the DIBAL comes from that, and sometimes it's abbreviated as DIBAL-H. Okay, so DIBAL reduction is quite interesting because during this whole process here, I wonder if I have an example of it. I do. What you've seen with esters and amides is that it actually goes through 2 rounds of reduction. So in this case here, if we want to reduce an ester, what happens is that you get first activation, you get nucleophilic attack, and then your transient compound in the middle is an aldehyde. And then that gets reduced again to an alcohol. So it goes through 2 rounds of reduction. But sometimes maybe you want to reduce something like an ester, but you only want to reduce it to the aldehyde. Maybe you don't want to reduce it fully to the primary alcohol. And if you use any of these reagents here, you know that you can't stop it. So is there a system or is there a molecule in place that can actually reduce things like esters or amides and actually stop at the intermediate stage here, in this case the aldehyde? that would be very convenient because aldehydes are very useful functional groups in organic chemistry. So this is where diisobutyl aluminum hydride comes into play. And let's see how this works and how this functions. So let's draw an ester, and let's draw a DIBAL-H. Now, this aluminum here is neutral, right? So it's not very nucleophilic. And this ester here is not that electrophilic either. So similar to the BH3, I want you to think of how these two can get together and can get activated. So this electron-rich substrate, the electrons from the bridging, or from this oxygen from the ester, is very likely to come down. And then like we saw with BH3, the pi bond will break and form an oxygen, in this case, aluminum bond. And then what you generate is now a negatively charged aluminum and a positively charged oxygen here. So what you have are now good ingredients for intramolecular nucleophile, intramolecular electrophile. So like we saw with BH3, now you can set up a system where you get intramolecular hydride attack and you move electrons up to that oxygen. I'll put in the hydrogen here so we know where it came from. Okay, so this is your tetrahedral intermediate. And what's going to happen is that you're going to now form a pi bond. You're going to release off your ethoxy group, and you're going to generate this intermediate, which looks very much like an aldehyde. Okay, this aluminum is no longer nucleophilic. It's neutral, and there's no hydrides attached to it. So what happens here is that during your workup step, okay, so this would be like 1. During your workup step, you're going to have water come in, and then this water will react at that aluminum and push electrons back to the oxygen, thus making your final product, which is an aldehyde. So DIBAL-H has the potential, or it actually does it very well, to take esters and go to the aldehyde. You have to do this at cold temperatures, because if you do heat up the system, you do run the risk of the aldehyde reacting with the DIBAL, okay? But you can control it if you're careful with your equivalents and you monitor and stop the reaction and quench it at the right time. So it's a very handy reaction, as I said, if you want to have an ester and stop at the aldehyde. So let's add that reaction right here. So here's an ester. DIBAL-H. Typically you want to do these at pretty cold temperatures like -70 or -78. And then you'll have a workup step. And this will give you and help you stop at the aldehyde. So yeah, like BH3, it reduces electron-rich carbonyl groups. So it works very well with things like esters, and DIBAL reduction also works with amides. So I'll just make a note here, DIBAL aluminum hydride reacts well such as esters and amides. Okay, so what I'd like to do is, we've learned a lot of hydride reducing reagents. I'd like to just take a few moments and summarize all these different ones and ask how they react with different functional groups across the board. So we're going to generate a table here. So just bear with me a couple minutes as I erase this board up here. So take a quick bio break if you have to. So what you can see is I'm just going to make a table with different reactive functional groups. And then we're going to just look at the different hydride reagents and whether they work or are compatible or not. So I got 1, 2, 3, 4, 5 different hydride reagents. Okay, all right, so looking good. So why don't we start with what we know? So I'm going to draw different hydride reagents. This is sodium borohydride. Let's draw lithium borohydride. Let's draw lithium aluminum hydride. And then let's draw BH3. We'll leave this one blank for just a second. And why don't we fill out what we know in terms of the reactivity of all these different functional groups. And if we don't know, we can make at least some educated guesses. So I got some chalk here, and why don't we just start with sodium borohydride with aldehydes. Okay, we studied that. All right, so sodium borohydride will reduce aldehydes for sure, right? We talked about that. So let's do reduces. So let's have a little key here. So R is equal to, it reduces. Okay, so sodium borohydride reduces aldehydes. Does it reduce ketones? Yes, it does. Does it reduce esters? Sort of, not really. It's not very productive. It can be very slow and sluggish. Often it just doesn't work. So but I'm not going to say it never works. So what we're going to do is write reduces very slowly. And then we have amides and carboxylic acid. So those actually will never get reduced. So not reduced, not reduced. Okay, let's look at lithium aluminum hydride. So we'll just skip lithium borohydride for just a second. We know that this will reduce aldehydes, you bet. It will reduce ketones for sure. It's also going to reduce esters. It's going to reduce amides. Carboxylic acids, again, it's a little bit unreliable. You can imagine that the first step that's going to happen is you're going to generate acid-base chemistry, and then you're going to have a very non-electrophilic carboxylate, resin-stabilized carboxylate. So this will reduce very slowly. Let's look at lithium borhydride. So, lithium borhydride, yes, it will reduce aldehydes, it will reduce ketones. Esters, it does reduce. We went through that mechanism today. Amides, not so great, but never say never. It will do it very slowly, or poor yields, or very sluggish. And then carboxylic acids does not reduce. Okay, now BH3 we just learned today is good at electron-rich substrates. So things like carboxylic acid and amides, it actually works quite nicely. With esters, sort of, not really. Okay, so it reduces very slowly. And then for ketones and aldehydes, we're essentially going to say not reduced. And I left a few blank spots, as you can see. So what I'm going to put here is something called sodium cyanoborohydride, and we'll talk about this in just a second. But before we do that, let's look at this amine here. So this is an amine. This is actually really, really electrophilic, more electrophilic than the aldehyde. And so what happens is that you can imagine your sodium borhydride is going to reduce that very easily. Lithium borhydride, no problem. Lithium aluminum hydride, no problem. BH3, not really. I mean, you might find a few exceptions, but let's essentially say no, it's not going to do that. Sodium borhydride, sodium cyanoborohydride, looks like this. Here you have a nitrile group attached to this negative boron. So instead of BH4, you have the cyano group. And if you compare the nucleophilic strength of this compound versus BH4, which one's going to be a stronger nucleophile? This is a cyano group. You can see electron density moving this way. Good electron withdrawing group. So what that means is that this is a more stable compound, therefore less reactive. So where this compound comes into play is that it's really good at reducing imines, minium ions, but maybe not so great at reducing aldehydes. So you might want to have a situation where you want to reduce this group, but not let it touch things like aldehydes or ketones. So it just reduces very slowly. It's really not efficient at all. And then no reaction for the ester, amide, and the carboxylic acid. And then finally, I don't have room for DIBAL, or maybe I can put it in. The DIBAL, yeah, let's put it in. The DIBAL-H doesn't touch amines, aldehydes. You know, you would never use this for aldehydes, so I'll just put reduces very slowly, reduces very slowly. And then this will reduce esters and amides, right? But this will stop at the aldehyde. Same with the amide here. And then for carboxylic acids, it doesn't work very well. Okay, so I hope that you found this unit on hydride reducing agents very informative, and I hope you enjoyed it from a mechanistic point of view, but I also hope that you can see the power of chemoselectivity in these different reagents, so we can fine-tune the control of organic molecules depending on what functional groups are attached. Okay, I hope you enjoyed that, and see you next lecture.